Hello, welcome students. I am Rekha Thorat, Associate Professor. Today we will discuss on the first topic of paper 7 of semester 4, real analysis 2. Name of this paper 7 is real analysis 2, and this paper 7 code for this paper 7 is DSC 5D. This is paper 7 of semester 4, real analysis 2. First topic is sequence and operations on sequence. Let us consider the definition of sequence. Sequence is a function whose domain is set of natural numbers and codomain is set of real numbers. That means sequence is a function from set of natural numbers to set of real numbers. This sequence is usually denoted by, in bracket, that means sequence Sn, n going from 1 to infinity, or in this bracket Sn, n going from 1 to infinity, or simply sequence Sn. And nth term of sequence is denoted by Sn. For example, let us consider first example. Sequence Sn equal to sequence n square equal to, when n is equal to 1, n square means first term is 1. When n is equal to 2, n square, that is 2 square is 4. When n equal to 3, n square, that is 3 square is 9. When n equal to 4, there must be 16. After 9, there must be 16 term. 4 square is 16. And then when n equal to 5, the term is 5 square, that is 25, and so on. Dash 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 n square dash dash dash. This is infinite sequence. Consider next example, sequence Sn equal to 1 upon sequence 1 upon n equal to, when n is equal to 1, we get 1 upon 1, that is 1. When n is equal to 2, we get 1 upon n, that is 1 upon 2. When n is equal to 3, we get 1 upon n, that is 1 upon 3. When n is equal to 4, we get 1 upon 4. Dash 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 1 upon n dash dash dash, bracket complete. Now consider next example, sequence Sn equal to sequence n upon n plus 1 equal to sequence, take n equal to 1, so that 1 upon 1 plus 1, that is 1 half, comma, and take n equal to 2, so that we get 2 upon 2 plus 1, that is 2 by 3, comma, take n equal to 3, so that we get 3 upon 3 plus 1, that is 3 by 4, comma, dash dash dash, and the term is n upon n plus 1, comma, dash dash dash, bracket complete. Now consider the example, sequence Sn equal to sequence 1 equal to sequence 1 1 1 dash dash dash, and the term is 1, comma, dash dash dash. Now we consider the definition of subsequence of sequence. Let S equal to sequence Sn be a sequence of real numbers, and capital N equal to sequence Ni I going from 1 to infinity. B, subsequence of set of natural numbers. Then the composite function SON is called subsequence of S and is defined as SON of I equal to S of Ni, S in bracket Ni bracket complete equal to S in bracket Ni bracket complete equal to Sni. Hence, S composition N, that is SON, equal to sequence Sni, I going from 1 to infinity. Let us consider one example. If S equal to sequence Sn equal to sequence n square and going from 1 to infinity, and n equal to sequence ni equal to sequence 2i minus 1, which is subsequence of this sequence Sn, I belongs to n, then find S composition n. Let us consider the solution of this example. We have given that S equal to sequence Sn equal to sequence n square and going from 1 to infinity, and capital N equal to sequence ni equal to sequence 2i minus 1, I belongs to n. Hence, S composition n. Hence, the subsequence of sequence Sn will be S composition n equal to sequence Sni, I going from 1 to infinity, equal to sequence ni square equal to sequence in bracket 2i minus 1 bracket square. Since we have given this term, bracket complete, I going from 1 to infinity, so that we get S composition n equal to, for n equal to 1 we get, I equal to 1 we get 2 minus 1, that is 1 square, that is 1. For I equal to 2 we get 4 minus 1, that is 3 square, that is 9. For I equal to 3 we get 6 minus 1, that is 5 square, that is 25, and so on, and the term is 2i minus 1 bracket square comma dash dash dash. Now consider another example. If S equal to sequence Si, if S equal to sequence Sn equal to sequence square root of n going from 1 to infinity, and n equal to sequence ni equal to sequence I raised to 4, I belongs to n, then find S composition n. Let us consider the solution of this example. We have given that S equal to sequence Sn equal to sequence square root of n going from 1 to infinity, and capital N equal to sequence ni equal to sequence I raised to 4, I belongs to n. Hence, S composition n equal to sequence Sni equal to square root of ni equal to square root of ni means I raised to 4, square root of I raised to 4 equal to sequence square root of I raised to 4 equal to sequence I square, I going from 1 to infinity. For I equal to 1 we get 1. For I equal to 2 we get 2 square, that is 4. For I equal to 3 we get 3 square, that is 9, and so on. There must be here 16. For I equal to 4 there is 4 square, so that there is 4 square is 16. For I equal to 5 we get 5 square, that is 25 dash dash dash, and the term is I, so that I square comma dash dash dash. Now we consider the definition of limit of a sequence. Let sequence Sn be the sequence of real numbers. We say that the sequence Sn has the limit L if for given epsilon greater than 0 there is a positive integer n such that modulus of Sn minus L is less than epsilon for n greater than equal to capital N. If sequence Sn n going from 1 to infinity has limit L, we write limit of Sn as n tends to infinity equal to L. Now consider the convergence of this sequence. First consider the definition. If the sequence of real number Sn has the limit L, we say that sequence Sn converges to L. If sequence Sn does not have a limit, then we say that sequence Sn is divergent. Now we consider some examples on convergence of sequences. Consider first example. Sequence n square upon n plus 5. We have to find the convergence of this sequence. Let sequence Sn equal to sequence n square upon n plus 5. Hence, we denote Sn equal to n square upon n plus 5. Hence, by taking limit of both sides as n tends to infinity, we get limit of Sn as n tends to infinity equal to limit n tends to infinity of n square upon n plus 5 equal to limit n tends to infinity n square upon taking n common, we get n into bracket 1 plus 5 by n equal to limit n tends to infinity, 1 n cancels, so that we get n upon 1 plus 5 by n, and as n tends to infinity we get infinity upon 1 plus 5 upon infinity, that is 0, and infinity upon 1 is infinity. Hence, the given sequence is divergent. Now we consider another example. Here we have to find the convergence of the sequence n upon n plus 1. Let sequence Sn equal to sequence n upon n plus 1. Here we denote Sn equal to n upon n plus 1. Now we take the limit of both sides of this Sn upon n plus 1 as n tends to infinity. Hence, limit of Sn as n tends to infinity equal to limit n tends to infinity of n upon n plus 1 equal to limit n tends to infinity of, take n common from numerator and denominator, so that we get n into bracket 1, and in denominator take n common, so that we get n into bracket 1 plus 1 upon n. Cancelling n, we get limit of Sn as n tends to infinity equal to 1 upon 1 plus 0, which is equal to 1. Thus, limit is finite, limit exists. Hence, the limit of this sequence is 1. Hence, given sequence is convergent. In first example, limit is infinity, so that limit is not finite, limit does not exist. Hence, the sequence n square upon n plus 5 is divergent sequence. But in this second example, limit of sequence n upon n plus 1 is finite limit, that is 1, and this limit exists. Hence, the sequence n upon n plus 1 is convergent. Thus, given sequence is n upon n plus 1 is a convergent sequence. Thank you.